Welcome back. This is section 9.5, Medical Applications Using Radioactivity, part of chapter 9. And so this is what some of you have been waiting for with bated breath. And we're going to actually talk about how we apply this information in the medical profession. Radioisotopes with short half-lives are going to be used in medicine because we don't want them hanging out in our body being radioactive, right? They have the same chemistry as the non-radioactive version, and so we can add them and then use their radioactive characteristics to allow us to see where the normal atom would normally go. And so in organs of the body, they will give off this radiation, and then we can actually get an image based on the energy that they are giving off. And these are just some of the different applications, you know, and we've talked about this. This is gold 198, cesium 141 or 131, and they're used because they tend to deposit in certain areas. Like I mentioned, I-125, which is good for the thyroid because it will go directly to that and really light that up. There are several that they've discovered for prostate. Strontium, which is a good one. Technetium, which is a good one for bones and some of the other softer tissues. And so I'm going to show you a little bit about these different treatments and then what they're using. So if you've ever had this, you know you go in and you drink this stuff, or they could inject it into you directly. And so when you do that, the radiologist determines the level and location. Is it set right now for this radiography? And so the scanner, once this radioactivity is set, will move very slowly across the area where that's been absorbed, and then the gamma rays that are being emitted will be exposing some type of photographic plate. They're not necessarily X-rays, right, because some of them are not that energetic, but they give you a scan of the organ, and so they can pick that up. Scans are used to determine where this has accumulated in the organ, and if you notice where they're shooting her and then the shape of this is obviously your thyroid, and they are looking at the accumulation of the iodine 131, and so they're seeing these, and then they will like touch these spots that they've been looking for, and to see if the thyroid is acting normally in its uptake of iodine. And so it's a really good tool for thyroid issues. Positron emission tomography, or a PET scan, is where they use positron emitters that have, of course, short half-lives for brain metabolism, blood flow through the heart. You can use carbon, oxygen, nitrogen, and even fluorine for this. And here's the example of fluorine as it's emitting the positrons. And basically, the positrons will combine with the electrons and produce the gamma rays, and then they are detected by the computers, and you get this great 3D image of a PET scan. And this has opened a lot of doors with brain scans. This particular one is showing you normal on this side versus an Alzheimer's scan on the right hand side, and they can tell by the differences in colors, activity, and which chemicals are being taken up, and more importantly, in the case of an Alzheimer's patient, probably where the material does not get into an area and where you would have less active areas. So they can read that, and then they can see how much damage has actually been done. Computed tomography, or a CT scan, they used to call them CAT scans, but they've come a long way. This actually uses X-ray, 30,000 X-ray beams that are directed at your brain in different layers. It's not as bad as it sounds, but because your tissue has different densities, they can assign colors to the different layers, and then they can give you this kind of three-dimensional look. And you can tell anomalies in the brain well, a trained person can, by looking at these images and seeing if you have like a really dense mass or something accumulating in tissue that should not be there. MRIs are like everybody seems to be getting them in their offices these days. It does not involve X-ray radiation, so you do not have to have that radioactivity issue. It's the least invasive method, and it's based on using a strong magnetic field and exciting some protons with that. And the energy that you're absorbing is converted to color, and it also gives you these really good images of the body. Here is your lungs, and that's the left ventricle of your heart. And so, as you can see, it gives you a really good picture of circulation and things like that, and even some bone and other soft tissue. Depends on the settings for it, but it's you don't have to ingest anything. It doesn't have to give you you know, any type of real bad nuclear type materials. All right, so in this learning check, you're supposed to decide which of the radioisotopes would be most likely to be used in nuclear medicine. Remember why something is a good candidate. Okay. The first one, potassium-40, its half-life is 1.3 times 10 to the 9 years. Would that be a good candidate or not? No. Not likely, because it has a really long half-life, doesn't it? Years is not good. We don't want it hanging around in our body. Okay. Potassium-42 has a half-life, though, of only 12 hours, and so it, on the other hand, is a good candidate for medical applications. And then I-131, we've already seen, has a short enough half-life so that it can also be used. So hours and a few days, not too bad. Years, no, we're not going to use that, right? And that's all we have of Section 9.5 in the medical applications. I hope you enjoyed this section.